Hello everyone, welcome back. Good morning. Yeah, hello. Good morning everyone. Welcome back. We have another exciting session prepared for you today. And today it's going to be a hands-on session on how to use PennyLane for quantum algorithm development. It's very exciting. So for this, we have our next speaker with us today. Our next speaker is someone who needs no introduction for those of you who have been with us in previous WISER programs. And for those of you who are joining us for the first time, you're in for a treat. Catalina is wonderful, and a little bit more about her. Catalina is the Quantum Community Manager at Xanadu, where she works closely with researchers around the world to help them leverage PennyLane and ensures that it remains a premium software tool for quantum computing. She has been the driving force in quantum education, leading PennyLane's educational initiatives, organizing events like QHack and Quantum Software 2.0 workshop, and giving talks and workshops globally. Before Xanadu, she was an IBM Quantum Ambassador, so she brings in perspectives from two of the most influential organizations in the quantum ecosystem. So Catalina has been a wonderful part of the WISER community across multiple programs, and we are so happy to have her back with us this year again. Please welcome me in joining Catalina. Over to you, Catalina.
Thank you very much. It's a pleasure to be here. Excited to be part of this program again. As I was telling the organizers, you're a wonderful community. I love how interactive you are and how much you learn, also how much the program has advanced in the past few years. So today you're in for a treat. We're going to be using a lot of reactions. I love seeing that you're already using them. So those of you who are joining me for the first time, I'm going to keep you on your toes. I'm going to be asking you questions. You can answer them on the Discord. And I'm also going to be asking you to share, to use reactions here in the chat. So before we begin, give me a reaction if you have already used PennyLane. If you have already used PennyLane, show me a reaction. Okay, quite a few. Anybody else? All right. Now, I see the X. If you have never used PennyLane, you can add an X. If you have never used PennyLane, you can add the X reaction. Okay, still a few. All right, so we're gonna do a little bit of an intro to what PennyLane is. For those of you who already know, this will be a recap at the beginning, but believe me, there's gonna be new content at the end, so don't jump out. Even if it feels repeated for those of you who already know PennyLane, you can answer the questions from the others in the Discord if they have any. All right, so let's start. Let me start sharing my screen. All right, so today the talk is going to be about this new framework, train classical, deploy quantum. Historically, you've always heard kind of this competition, if we can say, right? I'm going to do some quantum program, but can it be classically simulatable? Is there something here where quantum can actually help? And so this new framework says, if you can do things classically, that's great. It's cheaper, it's better, let's do everything that we can classically, and let's use the quantum computer for what it's really good at. And so if you can do things like training classically, this reduces a lot of the overheads. But if you want to sample, for example, from a really complicated probability distribution or from a really complicated problem, we want to take one sample. Maybe this is what we can use the quantum computer for. So this is kind of what we're going to get to at the end. Before, they already said my intro. I work mostly with researchers now. So I still do a big part of our work with the community, like being here with you, but I focus a lot on research because we care a lot about bringing the latest research quickly into PennyLane. So PennyLane is a software. It is always at the forefront of the state of the art of where quantum computing is. So a lot of my job today is talking to researchers, understanding what they do, and seeing how the tools that we have in PennyLane can help them for their research and how we can bring their research into PennyLane. We also do a lot of promotion, like we like to highlight good research. So this is a little bit of what I do, being able to make that bridge between Xanadu and this outside world. So the hello world first, for those of you who have never used PennyLane, this is built for it to be Python native. Like if you already know Python, then this will feel very natural for you. And then we'll go into the core of today. So can anybody tell me why we need quantum computing? Let's start with the Discord. Let's get you all started. Why do we need quantum computing? Some of you are typing. Let me see those answers. Just a few words. You don't have to write a long answer. I don't want to give you the spoilers. Okay, computations to decrease computation, to solve NP-hard problems, optimization, combinatorial problems, solve problems that cannot be solved by classical computing, or workers study the quantum system. Yes, absolutely. There are a lot of big areas, a lot of big industries that can be, or you can use quantum computing. How you do it is very important, right? The details are key. So at Xanadu, for example, we do research in algorithms, for example, for batteries, for solar cells, for semiconductors, recently for chemistry as well, for medicine as well. So all of these are within the chemistry area, but we also have a team that works on quantum machine learning. They are at different levels. There's still a lot of exploratory work. It's not all answered. And for us, everything that guides what we do is our mission. So we want to build quantum computers that are large. If you want to build quantum computers that solve useful problems, they need to be large scale. That is why we focus on photonics. So today we're not going to focus on the hardware. You can ask me questions later about the hardware, but I can tell you we use a mini photon approach. Basically, we use beams of light and we modify it on chip to do this quantum computation. We're based in Canada. We're proud Canadian. And this year is our 10-year anniversary of Xanadu. So this mission of making quantum computers that are useful and available to people everywhere, this is part of why I'm here today, helping you, sharing a little bit of what we know with you. And as I mentioned, we do everything from the hardware to the education and training. And of course, in the middle, we have the research and algorithms and applications and the software. So PennyLane, we want PennyLane to help you all the way from inspiring you to do new things to implementing them. And so this is why you'll see a lot of this education material coming straight from the research and into your hands. So leverage it, use it. All of this is free. So use it as, use it for your own problems and solutions. It is open source, meaning the code is online, free to use. Something that I really like is that people make new software based on PennyLane. So at the end, I'm gonna share one, for example, that it's a project built in a university. They built this layer on top of PennyLane. They use PennyLane as the base, but then they grew on top of that. This is something that open source allows. And it's designed in general for quantum computing, not only for quantum machine learning. So hopefully after today, you will remember that. If you forget everything today, that's okay. All of the answers are in PennyLane.ai, and they will help you. They will give you the resources for quantum computing in general, beyond optimization, if you're interested. So we emphasize this because it's a common misconception, because most people hear PennyLane is just for quantum machine learning, but it's actually much more. So you will see that recently we changed the way we import PennyLane. So instead of import PennyLane as QML, we now import PennyLane as QP. That stands for quantum programming. Import PennyLane as QP to remember that you can use PennyLane for much more than QML. Now, it's up to you. Honestly, this is personal preference. You can keep importing PennyLane as QML, or you can change it, or you can import it as something else if you prefer. This is more what you will see in our education resources, in our demos, in our content in general. So who's hearing this for the first time? Give me a reaction if this is the first time you're hearing about this new change to import PennyLane as QP. Yeah, quite a few. Good that you joined here today then. All right. In terms of education, we have university partners all over the world. If you know of a university that is using PennyLane or wants to use PennyLane, you can also contact us. On PennyLane.ai, we have a an education page. You can contact us there, or you can contact us on the discussion forum. So I'm going to share the link in the Discord. I think I have a copy, so I can share it now. This is where you can discuss with the community, ask questions. It's mostly used for questions. So if you want to contact us with your university, this is a good place to message us, or in the PennyLane.ai in the education page that we have, our teach page. Now, maybe the only thing you had heard now is PennyLane. I've been repeating it so much, but PennyLane is a full ecosystem, right? So it's an open source library, but it's connected to other libraries. So Lightning, for example, is our series of high-performance simulators. Catalyst is our compiler, and compilation is going to be very important because our programs are going to get so big that our classical computers maybe cannot even hold them, right? The bottleneck is not always on the hardware. I know we constantly think the quantum computers are too small so far or too noisy, but the software still needs to keep improving. So we're doing a lot of work in compilation. If you are into the classical world of compilation or high performance computing, maybe this is something you have heard about. A very important part of the ecosystem. And now the other thing that if you're new to PennyLane is you can actually run PennyLane in many different platforms. PennyLane was not designed to run on Xanadu's hardware specifically. It was designed to run, everywhere. It was designed to run wherever you want to run. So we have plugins. You can run it on different devices from different ways of working. It's not only designed for photonics. And if you want to learn more about that, PennyLane.ai has all the answers. All right, this is a little bit into the details, right? So far, give me, if you have any questions, let me check the Discord. Okay, mix of classical and quantum. Yes, but in this case, the hybrid compilation is all about, it's not only about mixing the classical and quantum program, but also the optimizations that you do at the moment of compilation. So when you do this compilation and you use the classical rules, for example, let's lower this to machine level and make it as efficient as possible. But also let's remember that if you have two Hadamards next to each other, they cancel out. One Hadamard plus one Hadamard, they cancel out. That is a quantum optimization that you can do. And this can happen here within Catalyst. And so it goes beyond just like the design of the programs that can be hybrid. Okay, so let's move forward. One of the things that we have that I would recommend, this is like new things that you might want to use, are things like resource estimation. So as these programs get very large, maybe they will be too large to actually program. So here you see a circuit. For small programs, you can actually simulate them, draw them, write them up. But for very large programs, you may know the subroutines. Maybe you'll say, I want to have an adder, I want to have a QFT, I want to have quantum phase estimation. So these are subroutines that you can add to your program. But you want to know how many gates, how many qubits you would need to run these programs. That's where resource estimation works really well. It's not actually running the program, it's just understanding the pieces and how they combine together so that it can tell you, oh, you're going to need 10 to the 4 gates, right? Or you're going to need this other thing. So I'm going to show you an example of how this looks for a very small example. But hopefully this can help you analyze very large programs, even if you cannot run them. I told you a little bit about Catalyst. If you're interested in compilation, this is a very important area of research, not only at Xanadu, but in the world of quantum computing. And if you want to run on simulators, for example, you can use GPUs or CPUs or even supercomputers to run quantum programs. So let's get to the hello world. I'm going to ask you for another reaction. So who here, maybe for those of you who haven't used PennyLane, have you used Qiskit or some other quantum programming framework? Yes? Not everybody, but most of you. Okay. So PennyLane, as I mentioned at the beginning, is very based on Python. If you are writing a Python function, you just write def, the name of the function, and then if it takes any arguments, you add them here in the parentheses. So these are circuits, are quantum functions, we call them, are just Python functions that contain quantum gates in it. So you can add your Hadamars, your C-naughts, everything that you want, all of your quantum gates, and even some classical for and if loops. You can have classical processing within these Python functions that we call our quantum functions. Now, you will notice that in PennyLane, we talk about wires, right? Where are these wires coming from? These wires are these horizontal lines that we draw in our circuit. So maybe if I go back, you remember this big circuit, it has all of these horizontal wires, or you will call them qubits, but in PennyLane, we call them wires. This is because PennyLane was designed for many kinds of computation. So in some frameworks, they use Q modes instead of qubits, but we can still represent them as these horizontal wires. So for you, for all intents and purposes, when we say wires, it means qubits. For almost everything that you will do, these wires are really just qubits. And how do we create a quantum gate, or how do we apply it to our circuit? So we first start with the definition of our circuit. Then we add, QP dot name of your gate. In this case, it's an imaginary. It's not a real gate. It's a made up gate called bread, which acts on these two qubits. Qubit 0 and qubit 1. So then I added here between these parentheses, the argument that it takes is, okay, I'm going to add a bread gate. And where is it going to run? It's going to be added on qubits 0 and 1. So if I have more than one qubit, I add them between these square brackets. So this definition of my gate would go within the Python function. And at the end, it's important to measure. If you don't measure anything, then you lose your result, right? If you program your quantum computer but don't measure anything, you haven't really done anything. So we can measure with different types of measurements, probabilities. We can have the state. We can return the state. We can return counts. So these counts are saying how many zeros or ones did I get. So we have different options for measurement. Now let's go into the practice. I'm going to use a Google Colab. You can use QBraid, Google Colab, whatever your preferred option is. So I'm gonna go and share here my Google Colab. I'm gonna make it a little bit bigger for you. If you're, give me a reaction when you're ready. When you have your QBraid or Google Colab or your local installation of PennyLane, give me a reaction. Okay, we're getting there. I see. I think there's I'm not sure. Okay. All right. So getting ready. So let's start with the code. So the first thing we're gonna pip install PennyLane. It might take a second. It will give those of you who haven't opened your notebook, it will give you a second. Now I'm gonna start writing code. I'm going to import PennyLane as QP. So hopefully now your favorite library starting from today. If you're not sure if you're using the right version of PennyLane, go to PennyLane.ai. In the first page at the top, it says what is the current, the latest stable version, the most recent stable version. So if you're in doubt, am I using the right version? You can print qp.about. You can print qp.about and it will tell you here, this is the version you're using. Okay, so who remembers how we create these quantum functions? You can say it in the Discord. I'm sorry, I'm making you jump between the Discord and the code, but somebody's saying something about a NOT gate, but it's actually just like a Python function. So def, I'm gonna call it circuit, empty parentheses, because I'm not gonna take any arguments here. And now I'm gonna add my gate. So this is an X gate. I can call it just with qp.x. Now I need to tell it what wire to act on. So what qubit? It's gonna act on wires equals 0. This means it's gonna act on the first qubit, which is qubit 0. There is 0 indexed. And I'm going to measure something at the end. I'm gonna measure the probability. So I'm gonna return, the return value is the measurement, return qp.probs. And finally, I'm going to draw my circuit. So qp.draw underscore MPL. And now I'm gonna write circuit. And at the end, right after this qp.draw underscore MPL of my circuit, I'm gonna add some empty parentheses. And so when I run it, that's correct. I was able to run my first quantum circuit. Now I'm gonna run, well, technically, I just created my quantum function and I drew it. So I was able to create my first quantum function. Now I'm gonna create another one. I'm gonna call it circuit 2. So def circuit 2 qp dot, and I'm gonna act on 2 wires. So wires equals square brackets 0, 1, and I'm going to return again qp.probs, just because it's easy. I'm going to use this, but you can use other measurements later. If you're more advanced, you can try remembering other measurements. Now I'm going to go a little bit quicker now. It's going to get hard very soon. So, if you get confused or are not following, we'll have some time at the end for more questions. So qp.draw underscore MPL. This is how I'm going to draw with this matplotlib drawer. This uses matplotlib under the hood. I'm going to, pass the name of my quantum function. And in this case, again, empty parentheses, because I have no arguments. This takes no arguments. So these empty parentheses are added at the end. Okay, so I was able to draw, 2 circuits, one with just 1 qubit and one with 2 qubits. Now, so far we have used empty parentheses, but we can use parentheses that take arguments. So I'm going to define a circuit 3, and this is going to take two numbers. I'm going to call them X and Y. So these are parameters that I can add to my circuit. I'm going to add now 2 gates, 2 rotation gates. Each of them takes one angle. If you're going to rotate, you have the block sphere, you rotate by a certain angle. So I'm going to write qp.rx. This is my first gate. It first takes the angle. So in this case, our angle phi is going to be 0.1. or actually, sorry, it's going to be x. So I had my argument x here. It's going to define the rotation for my rx gate. And I'm going to apply this on wires equals 0. I'm going to just use my qubit number 0. Now I'm going to do qp.ry, and I'm going to add my y rotation, and I'm going to apply it on wires equals 0 again. So we can apply all of these gates on the same qubit or a different qubit. And I'm going to return qp.probs again, just to make it easy. And if you remember how to draw, write it here on the chat. I see that people are already writing it. Awesome. Great. So we're going to write qp draw underscore MPL. We're going to call circuit 3, but this time we're going to tell it what angles. So here I have X and Y. I'm going to say, okay, use 0.1 and 0.2 as the angles for these rotations. So our X is going to rotate X degrees, which is 0.1, and our Y is going to rotate Y degrees, which is 0.2, or Y radians. Technically, these are radians, not degrees. Now, in the picture that I had before, I had the angles. So it turns out I can actually use this draw MPL and I can customize it. So I can say, for example, circuit 3, comma, decimals equals 1. I can also customize the style. I can draw in PennyLane style in different colors. So this is really fun. I do encourage you to check out this draw MPL function. You can look it up in the documentation, for example, and yeah, you can have these fun drawing styles and other things. All right, so far, where have these circuits run? Can somebody tell me in the Discord, where have these circuits run so far? People say simulator. This is actually a trick question. They haven't technically run. I haven't ran these circuits. I have only defined them and I have only drawn them, but they haven't ran anywhere. So here we go into PennyLane 102. So we're going to run on what we call devices. So these devices tell you where that circuit runs. We're going to use simulators today, but you could use quantum hardware. This is where you actually define, the backend. So for those of you who are used to Qiskit, for example, they call them backends. We call them devices. The default qubit device is really good, especially for starting, but you can also use lightning.qubit device. You can create a device by just writing qp.device, and then you define the device with a string. So you just say the name of the device, which is a string. Now you have this device that you created and you have your circuit that you created, but the way that you join them together is with a Q node. So these Q nodes are this thing that kind of collects the things together. They're the glue between the device and the circuit. The most common way and the recommended way of creating Q nodes is with this at. This at is called a decorator, and it modifies the function that goes immediately below. So when you add at qp.qnode, and then here you add your dev, the device you just created, it modifies the circuit that goes immediately below. It's no longer a quantum function, and it's turned into what we call the Q node. Note that this at qp.qnode is written with lowercase q node. There's going to be another one that I'm going to show you later. But this is the way that you kind of tell the circuit where to run. You create the device, and then you add the Q node to put everything together. And now, once you have these Q nodes, and even before, with your quantum functions that we had before, you don't have to write gate by gate. You can use templates. So in this case, for example, we can use a basis embedding to embed a number. Let's say number 2 is in binary, it's 1, 0. So you can actually embed this in your quantum program in a very easy way without having to write everything gate by gate. So just to give you this picture of what a Q node is, it is like this blue box that connects the circuit to the device. So hopefully this kind of paints a little bit of a picture of the role that these Q nodes play. You could also add classical things inside of your circuit, but the main role of the Q node is to join this function on this device. So let's go back to the code. We're going to create this device. So dev equals qp.device, and we're going to add the name of the device as a string. So I'm going to call it default qubit. Now, to create this Q node, we use the decorator. So at qp.qnode, it takes this device. It can also take other information, but the main thing that you want to add here is the device. And now I have to write the quantum function immediately below. So I'm going to copy the one that I had from before. So circuit 3, I'm just going to copy it here. So far, now when I call circuit 3, it's going to be a Q node. It's no longer going to be a quantum function. So I'm gonna skip this for a second, but I'm gonna run circuit 3 just so that you can see. I'm gonna copy my angles that I had, 0.1, 0.2. So I'm just gonna run circuit 3. Yeah, actually I can write it 0.1, 0.2. We run it like we run a normal Python function, and I can hit Shift Enter and I get a result. Now, if you look carefully, these are very small rotations. So think of the Bloch sphere and you make these tiny rotations on X and Y. You're really close to the zero, to the north pole of the Bloch sphere. So really close to the zero state. And this is what you get here. What is the probability of getting a 0 or 1 in this qubit? Well, it's very, very likely that if you measure this qubit that is really close to 0, you will get a 0. All right, so this other way of creating Q node, I'm going to call this Q node 1. We're going to use qp.qnode with capital Q and capital N. So if you write Q node 1 equals qp.qnode, then you can add the quantum function that you're going to turn into a Q node. So let's use circuit 2. Here, circuit 2 was just my CNOT gate, and I'm going to have to tell it where it to run. So I add the function, the quantum function, and the device. And now if I want to run that Q node, so I'm gonna comment this, and I'm gonna run Q node 1. I can run Q node 1 in the same way as I ran circuit 3. So it's basically taking the same, well, actually in this case, circuit 2 doesn't take any arguments. So I can just run Q node 1. And because this takes 2 qubits, so let me go back and show you. This is circuit 2. When we turn it into Q node, now we can actually run it. And if you see the CNOT of something that starts in the 0 state is 0, right? You have 0 and 0, and you add a CNOT, and basically you're controlling over nothing. So the bottom one doesn't change either. So here we have the answer. The probability of measuring 0, 0 is 1. And the probability of measuring 0, 1, 1, 0, and 1, 1, they're all 0. Now here comes something very important, and it's the ordering of the numbers. So the first one is 0, 0, and then we go kind of where we start changing from the least significant qubits is the bottom one, the rightmost one. So 0, 0, 0, 1, 1, 0, and 1, 1. This is different from what other frameworks use. So Qiskit may use the opposite one. Be careful. Always do a simple test to remember what is the ordering of the answer. Because in Qiskit, for example, it might be the opposite. All right, so quickly going into devices, let me see if there are any questions. I think we're good. Okay, so now we're going to use Lightning Qubit. If we use Lightning Qubit, for example, dev_L equals qp.device, and I'm going to add these quotation marks, lightning.qubit. Now I'm going to say here, right after the name of the device, how many qubits it's going to have. So I'm going to say wires equals 2, for example. This means that it has 2 qubits, qubits 0 and qubit 1. So it's for other devices, for default qubit, you don't need to specify it. It will automatically know. Default qubit will automatically understand how many qubits are in your device. But for other devices, you will need to say how many qubits. For hardware, for example, you will need to use the number of qubits in the actual hardware device. All right, so this is the last section. We're gonna just do a quick template. So I'm gonna create this Q node at qp.qnode of dev, which was my default qubit device. I'm gonna create dev circuit 4. Now we can add a template. So my template can be, for example, my basis embedding, qp.basis embedding. And I can say, okay, I'm gonna embed a certain number. For example, I'm going to embed 0, 1, 0, and this is going to act on qubits 0. So wires equals 0, 1. So these are the qubits that it's going to act on. And the first number is basically what am I trying to embed? What information am I embedding in my quantum computer? All right, and then I can return a measurement. So qp.probes, for example. Oh, I need to add my return, and I can draw. So qp.draw_MPL of circuit 4. All right, I got, oh, sorry. State must be of length 2. Let me see where I messed up. Oh, I think I need an additional qubit. That's where I messed up. 0, 1, 0. There we go. So yeah, in this case, I couldn't really embed 3 qubits into 2. That's why it was giving me an error. But now I could, so all good. Now, really quickly, if we want to see what is happening inside, we can use a decomposition. So this is relatively new, and for those of you who haven't, it's relatively new. For those of you who already knew PennyLane, this will probably still be new. So I'm gonna call it decomp. This is our decomposed circuit. So qp.decompose. So I can decompose my circuit 4 into a set of gates. So I'm gonna choose the gate set, which is gonna be the Clifford plus T. So gates underscore sets equals qp dot gate sets dot here Clifford underscore T. So this is gonna create a new circuit that is the decomposition. And now I can draw it. So qp dot draw underscore MPL of this decomposed circuit, and I can also run it. I can also run the decomposed circuit if I want to. Okay, let's see. Right. So in this case, because I'm just embedding a one, just one, I only see this. If I wanted to see basically all the wires, I can do show all wires equals true. Okay, normally it should have worked, but it didn't, but it's okay. Normally it should show you all of the qubits there. So we took a little bit of time, but this was important to get everybody on the same page. So give me a reaction. Tell me how we're doing. How's everyone doing here? Good? Okay, awesome. All right, so there are a lot of more options that you can customize. There are many more simulators you can run, for example, on AMD GPUs. You can run on other GPUs from many different companies. And now we're going to look into when you should actually use a quantum computer. So something that has been happening for the past few years is we've been questioning, and it's very good that we've been questioning, is the way that we're doing quantum machine learning, for example, or variational algorithms, is it working? And the answer, most cases, is not really. So is there a way that we can do things differently? And there may be an answer. So it's still a very active area of research. It's very new. So there's still a lot of, we still don't know the answer, but I'm going to show you what the conclusions so far have been. This is research done by our team together with people outside of Xanadu. Let's think of classical machine learning for a minute. In classical machine learning, you have problems that are generative machine learning. For example, let's find a way to make the computer, I'll ask the computer to create handwritten numbers, right? Let's ask the AI to give me numbers that resemble what a human would write by hand. This is a generative machine learning problem in the sense that it's not classifying things, it's not telling you what bucket it lies in. It is telling you, okay, give me a number that comes from the same probability distribution as these, right? So you can model this problem of handwritten digits as a probability distribution. And then when you sample from it, you get something that should be similar. So if you get a dot, this probably doesn't come from the same distribution. This is not really a number. But the final one kind of does look like a 3, right? So you can think of it as it's actually coming from the same pool of numbers. So there's two things here. One is training this algorithm so that it can produce the right numbers. And the other one is sampling from that model and seeing one individual answer. So these two parts are distinct. One part is the training and the other part is the sampling. Now there are certain problems, so certain math problems, let's call it, or certain kinds of circuits that can be classically trainable easily, right? So at the beginning I said this used to be this generally is this competition between classical and quantum, but in this case, the fact that something is classically trainable, it's very good. It means that we can actually build these generative models, maybe not for the specific application. This is something that a classical computer can already do pretty well, but there could be other applications where this probability distribution, this model, is so complicated that maybe we cannot represent it properly with a classical computer. Or maybe the amount of data that we have for training is very small. And when we have not a lot of data, that makes it harder sometimes for the classical computer to build these models. So let's look at these specific kind of circuits. Now, this is just an example. There could be other circuits that follow a different pattern that are not necessarily IQP circuits. So these IQP circuits mean instantaneous quantum polynomial, and it's just a set of circuits that have some multi-controlled Z rotations, basically just some specific gates that take parameters and that act on either 1, 2, 3, or more qubits, right? So you have this kind of ansatz, this layout or this template where you can customize, where you're going to have 1 qubit gates or when you're going to have 2 qubit gates, and they all take some parameters. So this is just an example of the kind of circuits that you can train classically in an easy way. Now there's a catch. You can find the expectation value. The expectation value is kind of like the average. If you sampled many times, what is the average? You can find the expectation value classically easily, but you cannot necessarily sample easily. So basically, you can find the average of this probability distribution very easily, but you cannot necessarily find one of the numbers very easily. So you might get this average blob, but you don't know what any individual number would be. And this is where the quantum computer can actually help. The quantum computer can hold that model that you can sample from. But you first need to find the right angles. And that you can find with classical training because you can calculate this expectation value in an easy way classically. Now, in addition to the actual ansatz, to the gates that you have here in the middle, you have a measurement or a set of measurements, right? These are called the observables. So the gates in the middle, you call them the pattern. Often you call them the pattern or the gates. And the thing at the end, you call them the observable. We can measure in the Z basis, for example. You can measure in the X or Y basis as well. And the final aspect to this is you're going to add these Hadamard's at the beginning and at the end. So before and after all of these gates with these angles, you're going to add Hadamard's. And what this is going to do is that it's going to move you from direct space to Fourier space, basically from just like direct values into frequencies. And that's how this has become so powerful. So you are doing this training, this optimization, where your model is really kind of working in the frequency space, in the Fourier space, instead of working just in the direct numbers space. Quantum computers are really good at these kind of things. The quantum Fourier transform is one of the main things in something like Schur's algorithm. It's what makes it so powerful. So it is interesting to explore. There's still a lot to explore in this area, but at least knowing about it now and getting the chance to learn more about it, you're really well prepared for what's coming next. So we have a tutorial in PennyLane, but today we're also going to do this hands-on example. So remember, we're going to do 2 things. We're first going to technically we're going to do 3 things. We're going to create this ansatz. We're going to create these kind of this layout of gates and observables. Then we're going to train these gates. We're going to train these gates to find the ones that most resemble a specific answer that we want. So we're going to choose a simple loss function in this case, but I'm going to show you where you can find more, let's say, the next version of that, the most advanced version of that. No, just to give you a sense, like what kind of problems could this be useful for? In the paper that our team published, they tried it on genomic data. So I don't know the details of this. I would encourage you to read the paper, but they compared it to some classical options like a Boltzmann machine and a GAN, and the IQP model, so trained classically, performed very well. We didn't run this on an actual quantum computer, but this was more about the classical training. And it turns out that you could train it pretty well. So it's at least comparable to other options. And this is one example where you have very high dimensional data. And this was, let's say, a 805 qubit model. It doesn't mean that we ran on 805 qubits. This was classically trained, so just classical math. Now let's look at the code. So we're going to start here. You can use the same notebook if you want, or a different one. So I'm going to install Optax as well as PennyLane. So if you have the option, you can install Optax. If you don't, it's okay. You can just follow me. All right, I see there are some questions. I see you're answering your own questions. That's amazing. Okay, give me a reaction. How are we doing with understanding kind of the main idea of this IQP optimization or the string classical diploid quantum? Yes? Okay, good. Awesome. Perfect. All right, so I have installed PennyLane and Optax. Optax is just a JAX optimizer. So for this example, we're going to use JAX. If you have never used JAX, it will take a second, but it's very similar to NumPy. So JAX and NumPy are very similar. If you want, you can write the code with me. If not, I will share this later. So we'll share it in the Discord, and I think we can share it in the LMS that you have from Wiser. So we're gonna share this info if you want. But if you want to do live coding, this is the best. I really like it. So the things that we're gonna import, maybe you already imported PennyLane as QP. We're also gonna import JAX, and we are going to import jax.numpy as JNP. So this is the thing that is gonna be most like NumPy. And Optax is just a JAX optimizer. So we're not gonna use the optimizers within PennyLane, we're gonna use JAX. We're gonna create a seed. This JAX PRNG key is the same as a seed in NumPy. It helps us for reproducibility, so that when we run this many times, we get the same answer. So I'm gonna write here key equals jax.random.prng key 42 in parentheses. This is just any number. You can write 0 or whatever. Now we're gonna create these generators. The generators are this symbol of gates and observables. There's going to be an easier way to create it, which I'll show you at the end. But for now, we can write, I'm going to use 4 qubits, and then I'm going to use a set of gates. So up to you, you can use whatever gates you want. For example, I could also have written, and this could be a little simpler if you're doing the live coding. So I could write gates equals square parentheses, and then inside these square parentheses, I have new square parentheses separated by commas. So these are all of our different gates. Let's say I'm gonna have 4 gates. One is gonna be, I'm gonna add a gate on qubit 0. I'm gonna add a gate on qubit 0, 1. So this is going to be a 2-qubit gate. I'm going to add a gate on qubits 0, 1, 2. And I could have another gate. Wait, I think I have too many parentheses. I could have another gate, let's say, on qubit 1. So you can set the templates, the gates that you want. Now, having more gates gives you more option for expressing, more complicated models. But just for starters, you can just create these gates. Okay, I think I am missing some parentheses, so I'm just gonna add some extra parentheses for each one. Yeah. This one, doing it by hand like this is not so easy, but I'll show you a trick on making it easier at the end. But hopefully this gives you kind of the idea of the fact that you have 1, 2, 3 qubit gates up to the number of qubits. You could have 4 qubit gates as well. All right. Now that we have created our gates, the next thing that I mentioned is you create your observables. These observables are basically what you're going to measure. We're going to, in this case, use the Z basis. So we're going to measure basically kind of in the normal way that we always measure. And for that, we're going to create a JNP.array. This is a JAX NumPy array. Again, we're going to have this big square brackets. We can make it simpler. So if you just wanted one measurement, you could say observables equals JNP.array. And then in my square brackets, within it, I can add another square brackets with my observables. So 3, 3 means Z basis in the first qubit 0, Z basis in qubit 1, and then these 0, 0 mean no measurement on qubits 2 and 3. So this specific observable is Z is a poly product, meaning it's a multiplication of this joining of these observables. So if let me quickly go to the slides and show you the example of the observable that we had here. Here we had 5 qubits. This would be I, Z, Z, I, because we only have the Z measurement in 2 qubits. So in this case, I would have like 0, 3, 3, 0, 0. This is how I would represent this particular observable. Okay, so going back to this example, in this case, we just have 4 qubits. I'm going to create a more complicated array of observables, but you can use a simple one if you want. Okay, here I print them just so that you can see kind of how they look. All right, let's see how we're doing. And let me see the chat. Why we use the number 3 in Z basis? This is just a design choice, you know. X is 1 and Z is 3. So there's no particular reason. So that's just how it's written. Yeah, hopefully this answers. It's just how it's designed. Remember, this is new. So there's, when you're doing something that nobody has done before, you sometimes make decisions like Z is number 3, and that's it. All right, so now we're gonna do the calculation of the expectation values. So this is something that is gonna happen classically, and we're gonna start with some random parameters. So again, going back to the circuit, at the beginning, we don't know what the angles for these gates are gonna be. So we're gonna start with something random. So in JAX, you can use the jax.random.uniform. It will create this uniform distribution. The key is just the seed. It's just so that it's reproducible. And this shape is just so that you have enough parameters for all of the gates. So the length of this gates, it's just gonna allow us to have, the right number of parameters. Now, this is classical calculation, and there is something called like this Monte Carlo happening under the hood. So the math that this is built on is Monte Carlo. And so you're going to use this samples. This is not quantum samples. This is for the Monte Carlo. So all classical. This is not the same as shots. This is not the same as shots. This is classical samples for the Monte Carlo sampling, for the classical calculation. And now, once we have defined this, so the params equals jax.random.uniform of key, comma, shape, len gates, and then this comma, just to say that this just have one shape, and underscore samples equals 4,000. And now we're gonna use this functionality. So qp.qnn.iqp underscore exp val. So I know it's a mouthful, but it's basically IQP expectation value. This is a function designed specifically for that, for calculating the expectation value classically. It takes a few things. So the few things we created, the observables. So that's the kind of these measurements that we're gonna measure. It takes the parameters, these random parameters that I just created. It takes the gates. The gates is this nested list of telling me which wires are gonna apply our gates on. It takes the number of qubits, this number of Monte Carlo samples, and the key, just again for reproducibility. And it's going to output two things, the expectation values and the standard error. So something very important to note is that this is not going to give me an exact answer. This is not going to give me the exact simulation of that expectation value. The more samples that I have, the more precise it will be, but it's not going to be exactly exact. It's going to be an approximation. It's a good approximation. It's an unbiased estimator for those of you who like statistics, but it's not going to be exact. And so once I have this, I can print exp vals, and it will give me the expectation value for all of my measurements. So in my case, I have 6 measurements. So if you look here, I have 1, 2, 3, 4, 5, 6. I have 6 measurements, and I have 6 expectation values. So it's like, basically in the circuit, we just have 1 measurement, but in my case, we had 6 different observables, so 6 different measurements. All right, let me check the chat. How do we decide that 4,000 Monte Carlo samples are sufficient? Maybe somebody with more statistics will be able to find like the perfect way of knowing the samples. For me, I just know in this case it works. You can always, if you want to do the math, that's valid, but you could also just try, if you're not getting the right answer, you could try more. Basically, it depends on how much you're willing to tolerate error. Like if you're willing to tolerate a certain amount of error and smaller number of samples is fine, then you can use a smaller number of samples. But if you need something that is more precise, it depends on your problem really. And how to calculate the number of samples from your problem, that's probably a statistician's question. But in practice, you can probably just increase the number. It doesn't take too long to run. So for now, we're going to use 4,000. Now we got these answers, and I'm going to compare it with the exact simulation. So just to practice, let's use a lightning qubit device. So dev equals qp.device. And here in these, as a string, I say lightning.qubit. So this is the device I'm going to use. And it's going to use n underscore qubits. So in our case, it's 4 qubits. Now I create my qnode. So by now, everybody remembers how to create our qnodes. So add qp.qnode of dev. It attaches this device to the quantum function that goes immediately below. This function takes two arguments, the weights, or like basically the parameters, and the pattern, which is our pattern of gate. And so this IQP template, it just takes basically what it's doing. If remember when we used the basis embedding template in the previous example, where we had an X gate, we could encode a number as a set of X gates. In this case, we have this IQP template, which creates this, basically, it creates this template, and then you can add all of the information to your circuit. Note that it's different from the IQP XP-val. This EXP-val only calculates the expectation value. It does not allow you to actually draw the gate, for example. You cannot create a Q node with this EXP-val. Let me know if the difference is clear. Is it clear what is this difference between all of the kind of the two different options, the IQP template and the IQP-XVal? I see somebody is asking, how can we learn all of these from basics to advanced? I will show you where you can find the more advanced info. All right, so this IQP template, we have the weight, the number of wires, the number of qubits, and the pattern. That's all it takes. And for this Q node, this IQP exact Q node that I just created, I will return the expectation value of just one measurement. Just for the example, I'm just going to return the first expectation value that I had, which was the 3300, which is this ZZII. So the way that we can calculate it with a Q node is qp.expval. This is this other kind of measurement. So it's not probs. In the previous examples, we always use probs, but here I'm using expval, which stands for expectation value, which is kind of like this average. Then I have to add this multiplication. The ats that you see here, they are basically like matrix multiplications. They are no longer defining the Q node. So, you basically just add your observables, qp.z of 0, because this is qubit 0, qp.z of 1, because this is qubit 1, qubit.i of 2, is because this is for qubit 2, and qubit.i of 3, because qubit 3. And then you multiply them basically with these ats. Now that I have created my Q node, I can actually run the Q node. So remember that when you run a Q node, you just call it with the necessary arguments. So my weights are my parameters, and my pattern is my gates. I'm gonna call this EXPV. It's just the exact simulation of this expectation value. And I'm going to draw the circuit so that you can see it. So the exact expectation value is, in this case, 0.06. Let me see. Yeah, well, it should be kind of closer to the other number. If I want to have a more similar answer, I could try, 5,000 samples. Let me just make sure I'm running everything this properly. Okay, here I get 0.06. It's getting closer to the exact simulation, and this one is staying the same because it's the same. So for the person who asks, is 4,000 samples enough? I guess it depends. In this case, 4,000 was not enough for this particular observable, but if I add more, it gets closer to the number. So yeah, good question from the person who asked. Now that I have the exact calculation, remember that this is only using random parameters. Here I use some random parameters. So if I want to do the training, first I wanted to show you how this looks. So if you decompose, remember in the previous example, we used qp.decompose to decompose into a set of Clifford plus T gates. We decomposed our basis embedding into X gates. Now I can use this, a different gate set. So all qubit ops, it will decompose, for example, multi-RZ gates. So are these, let's say, kind of black boxes that we had before, these black boxes that are just these kind of things that have a parameter there. In reality, you can write them as multi-RZ gates. So a little bit of a complicated gate, but nothing too bad. All right. So now that you have this, you can sample. Remember that the point of using the quantum computer is to sample. So for this, we can set a number of shots. So if you wrote the program before, you can copy it again, you can copy paste. And the only thing you're going to add here is at qp.set_shots of 10. So this is going to say I'm going to run this simulation 10 times. If I were using an actual quantum computer, I would sample from it 10 times. And then I can just run the same thing. But in this case, I'm going to extract samples instead of an expectation value. So if you look here, I get ones and minus ones. This is because when you measure in the Z basis, the measurement of the Z observable, if you measure the 0 state, basically the positive Z basis, you get a +1. And if you measure the negative z basis, you get a -1. So these are the samples from these observables. I know that like if you're starting to learn quantum computing right now, you're going to say, wait, if you measure the positive z basis, that's the 0 state. What do you mean it's a +1? We're measuring a different thing. So I'm not measuring the state, 0 and 1 state. I'm measuring the poly z observable. And that gives me a +1 if I measure the positive z and a -1 if I measure the negative z. So I will show you where we can learn all of this, but for now, hopefully this gives you an idea that the expectation value is this number, with decimals, and the sample actually gives me, the sample from that observable. So an answer that would come from that observable itself. Now you can do training so that you can, for example, minimize the expectation value. Maybe for whatever reason, the way you encoded your problem, the expectation value encodes some kind of cost or loss. So this is where you would use training. I'm going to glance a little bit quicker here, but basically I'm going to create some random parameters, and I'm going to use the same IQPX val that I had before, but I'm going to wrap it in a new function that I'm going to call xval function. I'm going to use this just so that my xval function can take as argument the parameters so that I can train over these parameters. This is just one way of doing it, but there will be an easier one that I will show you later. So here I have my expectation value, and I can calculate them. Now I can create this loss function. So for my particular example, I'm going to minimize the sum of the expectation values. I want the sum to be as close as possible, as small as possible. And now I can use optax. So for those of you who used or imported optax, we can use this Atom optimizer. We can use others as well. There are many options of optimizers we can use. This is more of a classical, more a traditional optimization routine. You have an update step. This update step will find a new version of the parameters. Now for optax itself, it requires you to kind of keep track of this optimization's state or optimizer state. So I'm going to calculate the gradients and the loss value. I'm going to share this notebook later, so don't worry too much about the details here. The main thing is that I'm going to find these gradients, update the parameters, and apply those updates to find new parameters. And I'm going to print the answer every 5 steps, how the loss is going. So don't worry too much about this. This is not the important part. And finally, I can have this bigger optimization loop, this higher level optimization loop, where I start with some initialization of my optimizer with my random parameters. I calculate the new version of the parameters. I have a for loop for 100 iterations. I calculate a new iteration of the parameters after these 100. After these 100 iterations, I will have a new value of my parameters. Basically, that's the answer. And I will return this final version of those parameters. Okay, so let's run this. So I do get a loss that is decreasing. So I start with a loss of 1. Basically, my random parameters were doing whatever. And at the end, I get a loss of -2. It was decreasing, and it kind of to get smaller and smaller. The expectation values, I can see they're all negative. So indeed, it was actually doing something. So I was able to optimize or train classically these parameters to give me the expectation value that I want. Now we're going to go into PennyLane Labs, and this is the thing that I was hinting at. So PennyLane Labs is an experimental module of PennyLane. So one of the things that you love about PennyLane and that I love about PennyLane is that it doesn't break your code every 2 months, right? I know how frustrating that can be, and we really try to make PennyLane as stable as possible so that you're not going to iterate over your code so often. However, the research sometimes needs to evolve faster than what the main part of PennyLane does. So this is a sneak peek into this research or experimental side of PennyLane, where things can break between one version and the next. So here within qp.labs, between PennyLane and PennyLane.labs, you're going to see this thing called Fox. This may change name, but this is basically this train classical deploy quantum. So we may not keep the name Fox, but the main idea under this is these are all of these functionalities that are designed to help you train classical deploy quantum in an easier way. So today we worked a little bit in hard mode because I didn't want to overuse this experimental module, but I do want to share it with you so that you have it here. And you're going to see this workflow that uses easy functionality. For example, I can create all of my gates without having to create all of these square brackets and forgetting how the square brackets go. you can actually use this functionality, which is create lattice gates, which is part of Fox. And you just tell it how many rows, how many columns, and like what is the, like if I want maximum 2-qubit gates or 3-qubit gates, I can set it up here easily in just one line. Same for the observables. I can say I want to create observables in Z basis instead of having to remember that it's the number 3. I can use them, say, in the Z basis. So I just create this circuit configuration, and then I pass the circuit to configuration to this function build xval function, which I can already JAX it, for example. So this is classical compiled. So in way less steps, you can create this expectation value function that takes the parameters and gives you the answer for those expectation values. And this also has option for training. So instead of creating all of this complicated training with OpDAX, you can just use train directly from this Fox module, and it allows you to choose different optimizers, different configurations for your optimization. You do still have to define, for example, the loss function if you want something very particular. Let's say in this case you want to minimize the sum of the expectation values, you may need to define it. There is one, however, that is like really good, that it is very good if you want to compare probability distributions. Say, for example, you have this distribution that I mentioned. Maybe you have very few data or it's complicated for some reason, and you want to create a model in the quantum computer that you can sample from that gives you answers as if they came from that distribution. So you can use this MMD loss, maximum mean discrepancy, which is designed kind of for that, to reproduce a certain target probability distribution. So you can see all of the example here on how to use the specific loss function. So I would recommend that if you want to try this is a little bit more advanced and more experimental. This may change next time that you see it. Maybe everything will be different. But if you're curious about trying something that is really at the forefront of research, this is it. This is where you can find it. And so I will share the link in the Discord here so that you can have it. In any case, I will share a page later which contains all of the links that you need. All right, so I know this got hard quickly, but I just want to share one last thing, which is resource estimation, which I mentioned this is useful if you want to find information about your circuit without running it. So something within PennyLane is our estimator module, and you're probably going to hear about it a lot. Resource estimation is part of how we design quantum algorithms, right? So you joined the session today to learn how to design quantum algorithms, and you cannot really improve them if you don't know how big they are, how good they are. So this is one way that we can define, how big this algorithm that I designed is. So this PennyLane.estimator module, we're going to import it as QRE, quantum resource estimation. And within it, you have a lot of different options, like IQP, for example. You can calculate the resources for this IQP template. You just have to tell it the number of wires and the specific pattern. But in a second or less, you already have an answer of, okay, this is going to take this many gates, this many T-node gates, and a few other key information. The Hadamers, for example, if you remember, if you go back here, remember we had Hadamers at the beginning and at the end. So at the very least, you know that this is actually calculating the right number of Hadamers because that's 4 at the beginning and 4 at the end. So just to conclude here, PennyLane is one resource. It's one resource in your toolkit. You can use it if it's a thing for you. You can use something else. So you don't have to stick to PennyLane, but we do make sure that it's at the state of the art. So it's very likely that if you Google something that is, you're going to learn about this new thing like DQI. We're going to talk about we do a hands-on example on decoded quantum interferometry. You're going to see that PennyLane already has an example for that. So I do encourage you to check it out. If you're interested in doing a little bit more advanced things, you can use the demos. If you are learning about PennyLane only now, I would encourage you to use the PennyLane codebook. So in PennyLane.ai, you can look in the resources option, and maybe for this, it's easier to show you on the actual website here. You can go to the resources tab and you can look for the codebook. This is my favorite learning resource. You can start here. You're going to see this nice map that shows you all of the options that you have. If you already know about quantum, but not about PennyLane, then the PennyLane fundamentals is, would be my recommendation. If you're starting with quantum, then this introduction to quantum computing kind of learning path is good. And if you want to learn more about algorithms, or if you want to learn about error correction, noise, there are a lot of different additional options that you have here in the codebook. So this is my favorite learning resource. If you're doing other advanced stuff, you may want to go to the Quantum Compilation Hub. I mentioned compilation. We have a lot of different passes and tricks and options. So for compilation researchers or people who are interested in this is very, very useful. And there are a lot more other options. So definitely explore PennyLane. It has a lot of learning surprises. And one surprise for you is today we're announcing that we're going to have a PennyLane challenge that is going to give you a PennyLane Wiser Certificate of Achievement. So if you complete this challenge by July 15, 2026, so you have just a little bit over a month to complete this Schrodinger's cat challenge. I know you're learning a lot about optimization in this month. So this is a good chance for you to put that in practice and challenge yourself with something that can actually give you a certificate. You can share it on LinkedIn. All you need to do is to complete it before the set date. And you will need to submit the, there's a specific question. You're gonna need to answer some questions in the Wiser LMS. So nothing too complicated, just we're gonna need to know your PennyLane username so that we can give you the certificate, this kind of thing. So make sure that you complete the challenge before the date and you submit the information in the Wiser LMS. I called it the Wiser quiz, but it's really just the information so we can actually deliver the certificate. Let me know if you complete it. You can tag PennyLane in LinkedIn if you get the certificate. We love seeing those. And if you don't have a PennyLane account, then this is a really good opportunity to make one. You can create your own username, your profile. So I use my profile. It's great. This is where you will have your certificates awarded as well. So you will need your PennyLane account in order to earn that certificate. So this is your opportunity to create it and your opportunity to start exploring. Hopefully this gives you a lot of new ideas. Hopefully this is a new thing. I know it's hard to understand the first time. I can say it from experience. The first time somebody explained this to me, it sounded a little bit strange why you would train classical and deploy quantum. But the more you get used to the idea, it actually makes a lot of sense. So start from there. As always, if you're comparing to classical, make sure it's a fair comparison, but start exploring new applications and keep learning. So hopefully this gave you new ideas to, inspire you and hopefully help you with the implementation as well. So I know this was a lot, but let me know if you have any questions. Okay, somebody said, I'm a little confused about the role of the Q-node in the whole workflow. The role of the Q-node is to tell the quantum function where to run. That's the role. It's like this wrapper thing that tells it, okay, I'm going to run on this specific device. So in other frameworks, you're going to add the device directly into your circuit. Here, you can create your circuit in a flexible way. You can do a lot of things without needing to attach it to a specific backend or device. So that's the role of the Q-node. So for those of you wondering what these Q-nodes are all about, that's it. It's just the thing it's just the glue. Let me see. Anybody else? If you run the circuit multiple times, will it always give the same probabilities? So all of these things, because we're running classically, we can use a seed or a key. So these ensure that when I run this many times, the probabilities are going to be the same. However, in real life, no. In real life, if you don't have a seed, the probabilities can be very different. How is the translation different in PennyLane compared to Qiskit? You have different options in PennyLane. So we call them part of our compilation. So part of our compilation, we include the translation, but you can customize it a lot. So you don't have to stick with one specific thing. You have a lot of customizations, but the way it works is a little bit different. So if you have more questions like this, like how do I do translation in PennyLane, the discussion forum is the best place to ask. So here you see discuss.pennylane.ai. That would be my recommendation. I know you'll have a lot of questions right now, which is great. I love that. I mean, we did answer a few throughout, but there will always be more questions. So I will share this in the Discord, discuss.pennylane.ai, for things like, like how do I do the transpilation? That's the best place to ask. And somebody asked, where's the link to the challenge? Let me get it for you. So you can always go to PennyLane, the coding challenges section, but I will make it easy for you. Let me find the challenge. Here you have the link to the challenge, Schrodinger's cat. So no cheating for this month, no posting the answer online. Of course, it's up to you. We cannot really check, but it's really your own learning. So I encourage you to keep learning. And I know we're at time. So Rachel, thank you very much for the invitation. Thank you, everybody, for attending. I hope you liked the session today. And it's great to be part here in the community.
Thank you so much, Catalina. That was super great. I love the interactivity. I'm sure our participants also appreciated the ability to have that back and forth with you and are excited, hopefully, about your hackathon challenge. Everybody, the information shared here, the video, we will be editing it, downloading it, and uploading it to the online course before the end of the day, along with any other material links or content that Catalina mentioned and shared. So all of that will be available on the LMS, as well as the video being available on our YouTube channel for you to view. If you haven't gotten your LMS access or your Discord access, that shouldn't be very many of you at this point, but we are going back through to make sure everybody has what they need. We next week have a great lineup with additional speakers, so we're very excited to do next week. There'll be an email going out with all the information that you need for that after this session, and we encourage you to share what you're learning and what you're excited about on LinkedIn and tag us and use the hashtag UQ26. And we appreciate everybody's participation today. And again, thank you, Catalina. And we will see you all on Monday.
Thank you.